Hi there everybody, it's Mr. Pope from Wilmington Grammar School for Boys, and today we're going to be looking at coordinate geometry problems in 3 dimensions, and mainly looking at equations of planes, solving problems with planes, a few other geometrical thingamabobs, and revisiting lines a little bit in 3D. Okay, so let's remind ourselves, how do we work out the vector form of a line? Well, the vector form of a line is we'd have a line L would be, let's suppose some points A, B, C. That is a position vector A, B, C. And then you would add some arbitrary multiple of, say, another vector D, E, F. Okay, and if I was to draw this on a sketch in 3-dimensional space, then this vector here would be the A, B, C vector. And let's suppose I've got another point over here such that if I was to draw a line going through these 2 points like so, then to get from this point to this point would be the directional component DEF. Okay, and the idea is that to the equation of the line in vector form is just going to be you get from the origin to one point you know, like that. So let's call this point A, this point B, and this point O. Then in this case, I've got ABC, which is the vector O to A, and then I've got some multiple of the vector going from A to B. Okay, that's really simple. Okay, now in this course, let's expand on that a little bit, and let's have a look at the Cartesian form of a line. Okay, and all we're going to do now is we're going to say, right, okay, well, if I look at the x component, and if I read off the top line, that's just a plus lambda d. Okay, so we're just going to read them off. So y is going to be b plus lambda e, and then it's lol, and then z is, or z, I always forget which one's English or not, c plus lambda f. And then to get this in Cartesian form, or rather to get an equation for the line in Cartesian form in 3-dimensional space, what we're going to do is we're going to make lambda the subject of each of these things. And for the top one, if you realise, if I do x minus a over d, and then y minus b over e, and then z will be z minus c over f. And now that I've got all the lambdas equal to each other, I can now just write x minus a over d equals to y minus b over e, and that also equals to z minus c over f. So this would be the Cartesian equation of the line L over here. Notice how there's 2 equal signs, and you've got 3 things being equal to each other, and all those things are being equal to lambda at this current point in time. That's perfectly fine and acceptable. And going from a line in vector form to Cartesian form, we have the following results. So you need to be familiar with how to go from a Cartesian form to vector form and vice versa, and you need to be familiar with how to work with those 2 things. So I'm just going to move some space down. Okay. Now what I want to do is I want to do a similar thing, but now for a plane. And I'm going to do it in a similar kind of way. First of all, I'm going to look at the vector form. So let's consider what's going on for planes. Okay, and what do I mean by a plane? Well, imagine I've got my right-handed coordinate system. So this is x, this is y, this is z. So the way we do that is we stick out our right hand, and we say our fingers point in the x direction, and then if we close our hand to make a fist, then that's where the y direction is pointing, and then our right thumb is pointing upwards, that's where the z would be. It's just a way of orientating ourselves. So what do I mean by a plane? Well, imagine I've got an infinite sheet like this. Now it goes off forever in all of those directions, right? I've only just drawn a rectangle just to illustrate a point because I'd be here forever. But imagine a sheet that's kind of floating in free space. Now it might be floating at an angle, it might not, it might be floating vertically or horizontally or whatever. But the point is it's completely flat and it's a horizontal flat plane surface. Okay, well, for the vector equation, we treat it the same way like we did for the line. But as you'd expect, suppose we've got one point on the surface, let's say there, and we'll call this A. Then the first thing we're going to be doing is, well, we would generally denote pi, P for plane. Pi is the Greek letter for P. Usually it's pi. You don't have to. You could label it as R, it doesn't matter, but I'll probably leave it as P for pi for P, sorry. So we're going to go to some point A. So let's say that's the point A, B, C. So the first step is going from the origin to some point on A, like so. So let's say this is O to A. And now, with a plane, we've got to be a little bit more interesting. So if we know 3 points on the plane, let's say A, B, and C, then we could work out the vector A to B, and we could work out the vector A to C, and as long as they're not multiples of each other, then that's all the information we need, as long as they're not parallel. So actually we could add some amount of the vector A to B, and we could also add a different scalar parameter of another vector, and this one is A to C. Now it doesn't matter, this isn't unique by the way. I could have easily gone from O to B, and then B to A, and then B to C, and for the other combination as well. It literally does not matter. And let's just fill these with arbitrary constants just to, not spook you or anything. Let's call this LMN, because I don't want to LMN. Okay, so a plane in vector form has an equation like this, okay? And essentially you need that extra bit of information to help you with the fact that you're covering a space rather than a line. Okay, now, there's also something else. And what is that? Well, there's the Cartesian form of a plane. And you're probably thinking, right, okay, what is the Cartesian form of a plane? That's pretty simple. Oh, whoops. Well, what's going on here? Well, to do that, what we need to do is find a perpendicular vector that's not only perpendicular to AB, but perpendicular to AC, is perpendicular to the whole plane, and let's call this N for a normal vector. Okay, then the Cartesian equation of this plane, and then let's say this normal vector N has components N1, N2, N3, then it's very simple. It's going to be X times by N1 plus N2 lots of Y plus N3 lots of Z equals some constant. And that is the vector form, the Cartesian form of a plane. So there's a couple of things to unpack here. Why is that the case? Well, firstly, it's pretty common practice that planes are defined by their normal vectors. Why is that? Well, because if you was to give me a vector, and you used to say it was on the plane, that doesn't really tell me much. For example, if you give me the vector A to B, then I could think of another plane, for example, that like pops out of it like this at a different angle. Now it's slanting upwards. So giving me if I was to define a plane by one unique vector, i.e. define a plane with the least amount of information possible, then you can do that uniquely with a normal vector. And it's very simple. All you need is where that normal vector starts from, its origin point, the orientation of the normal vector, and I know that any point on a surface where the vector from that normal point to anywhere else forms a 90 degrees, that will map out the basis of this plane. Okay, and then if you look very closely, and I'll remind yourself what's going on here, n1x plus n2y plus n3z equals k, this is just n1, n2, n3 taken with the dot product of x, y, z, and this just equals a constant. That shouldn't be a surprise. Okay, so if I take the dot product of the normal vector with anything else, I will always get a constant. Okay, now the trick is going to be, how do I find that normal vector given that I've only got these two vectors here, DEF and LMN? And to do that, we're going to need a little trick in our toolbox, which I'm going to go over here, and this is called the vector or cross product. Okay, now what I'm going to do is I'm going to just cut to the chase and tell you that this is in further maths. The proof, however, the proof for it isn't required in further maths. You can just assume, you can assume this result. Okay, so I'm going to put a box around the vector product definition and how it works, and then when I go on to the next page, which is the proof, you don't have to worry about it. So what is the vector or cross product? Well, very easy. If I've got a vector, let's call it A, whoops, and I cross it with B, so it looks like A times B, but this is a cross, then this is just going to be the magnitude of A times the magnitude of B times by sine of the vector between A and B, and then this is times by n hat, and this n is the same as this n, and it's the normal vector, but it's the unit normal vector, so that's important. It's the normal vector, but only of length 1. So a unit just means length 1. That's length. Okay, so this is important. Okay, so put a pink thing around this. That's important. And you're probably thinking, right, okay, so what's going on here? Well, suppose we've got a coordinate system like this, and say here's my vector A popping out like this, so that's my A, and then let's say this is my vector B popping out like this. Then imagine I take a copy of this vector and I put it there, and I take a copy of the B vector and I put it here. Then this mod of A mod of B times sine of theta is actually the area of the parallelogram mapped out by the vector A and the vector B, which we're going to call R. So this is my R here. Let's use a different colour. Let's use orange. That's R. Oops. Okay, so a lot to take in. Why is that? Well, let's prove it. Okay, so how do I find the area of a parallelogram? Well, notice how I use sine of theta here. Well, theta is the angle between A and B, so it's this thing. And now notice if I drop a vertical from here, like so that's 90 degrees, then this black line, if you think about it, is the horizontal height, isn't it, of the parallelogram if you turn it sideways. I mean, if I take this object put it here. I take this object and I give it a spin. I turn all the letters round. Then this is the region R we want to find. This is the vector B, and this is the vector A still. Okay, well, okay, so what would the area of this parallelogram be? It will obviously be base, which is B, times by, this is the base, and then what would the height be? Well, it would be this opposite of this right angled triangle here. So opposite of hypotenuse, so sine of theta equals opposite, which is the height, divided by the hypotenuse, which is going to be the length of the vector A. And then clearly, if I multiply by the length of A and put it there, I'll get the height is sine of theta times by the mod of A, and then I'll whack that over to here. Then hopefully you can spot that these two things are the same as this over here. So at least that's diagnosed that bit correctly. Okay, fine. You're probably thinking, okay, it's the area of the parallelogram. Fine, I get that. Why is it I'm multiplying it by the unit normal vector? Why is that the case? And before we get into that, I need to remind you of a few things. One, let's deal with the 2 by 2 case for a second, and hopefully you'll see why it becomes true in higher dimensions. Okay. If I have a vector going this direction, which is say I, and I have a vector going in this direction, which is j, these are unit directions, unit vectors in that direction, then the area of that parallelogram, which is a square, is just going to be 1. Okay, and by the way, I is the column vector 1, 0, and j is the column vector 0, 1. Do you agree that if I combine these two to make 1, 0, 0, 1 like this, then the determinant of that, which we've seen before, is the area scale factor of the shape? And the determinant of this is just 1 times 1 over 0 times 0. Okay, which is clearly a 1. Okay, so that determinant, let's suppose I do something wackier. Let's suppose I multiply the j component by 3. So now it's got an extra 3 like that, so it's now 3i. So now it's going to be a longer and skinnier rectangle. So what's going to happen? This becomes 3i, this becomes a 3, this becomes a 3, and the area becomes a 3. The determinant is the thing that changes the area scale factor. And we kind of talked about this in last time stuff, but essentially what I'm talking about, and what I was hoping to remind you of, is the determinant of the matrix, the determinant of the matrix of what we're talking about here. So the determinant of, and then we'd have ax, ay, az, and then bx, by, bz, and really we'd need a cx, cy, cz. If we're talking in 3D, that would be the area of what's called the parallelepiped. And in 2 dimensions, if I had took the determinant of the x component of the vector A and the y component of the vector A and the x component of vector B and the y component of vector B, this would be the area of the parallelogram. Now, if we backtrack, what's a parallelepiped? And this is my best representation of trying to draw a 3D shape on a two-dimensional thing. Imagine a parallelogram, and now imagine that parallelogram is extended into 3-dimensional space. So what I'll try and do is I'll try and get parallel sides of the same colour. So if those two are black and those two are red, let's have these two of the same colour. These two, they're parallel, so they're the same colour. Now I've got these two are red, they're parallel. These two are red, they're parallel. So essentially, it looks like a cuboid, but these angles aren't necessarily 90 degrees. They might be 20 degrees and so on. The point is, it's kind of like a deformed cuboid. It's a three-dimensional parallelogram. Okay, if I was to draw a cuboid properly, then it'd be a rectangle like this, and then all the sides would be rectangles. Every single angle, that's 90, 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 and so on. Everything's 90, but with parallelepiped, it's not. So, need to show you where the unit normal comes into this. It's very simple. So why is it multiplied to get the unit normal? Okay, so suppose the vectors A and B are on my plane, and I want to find a new vector, which I'll call C, that is perpendicular to the plane. So what kind of properties does it satisfy? Well, we've only ever seen the scalar product, right? So what must that mean? It means that A dot C equals 0, and it also means B dot C equals to 0, right? Because C in remember that the scalar product is that if I've got A dot B, that is the length of A times by the length of B times by cosine of theta, and that will produce a scalar. That will produce a number k. It's called the scalar product because it outputs a scalar. The vector product is called the vector product because it outputs a vector. And it's also called the cross product because there's a cross here. Okay. So, what would it look like for A dot C equals to 0 and B dot C to equal to 0? Well, let's prove this. So, A we're going to find as having AX, AY, AZ. B is going to have the things BX, BY, BZ. And C is going to have the components CX, CY, and CZ. By the way, A, B, and C, X, Y, Z's, all these things here are just numbers, they're just constants, whereas these things here are vectors. Okay, it's an important distinction. Okay, so let's just compute the dot product. So A dot C is going to be AX CX plus AY CY plus AZ CZ, and this equals to 0. And similarly, if I do B dot C, it's going to be BX times by CX plus BY times by CY plus BZ times by CZ. Okay. Now, interesting thing's going to happen here. If I take this row and I multiply it by B1, and I take this row, I'll call it row 2, and I multiply it by A1, and I subtract them, then look what's going to happen. This becomes B1 this, B1 this, B1 this. This becomes A1 this, A1 this, and A1 this. And these two terms, when I subtract them, they're just going to cancel because I've got, sorry, not A1, lol, this is BX and AX. So this is AX, BX, 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 AX, AX. Okay, well, those two terms cancel. Then what we're going to have CY, lots of, and then I've got BX, AY minus, well, let's get it alphabetized. I've got AY BX minus AX BY plus, how many CZs do I have? I am going to have AZBX minus AXBZ equals to 0. And already, you know, you can tell there's some kind of determinant thing going on here. You've got the multiplication of two objects minus the product of another two objects. So you can already sniff there's going to be some kind of determinant thing going on here. The next thing to do with our proof, well, we'll set this quantity equal to this quantity. Well, I'll show you what I mean. I'll take that to the other side. So if I take it to the other side, then this equals minus this. And then if I fiddle around with the brackets a little bit, I can swap the order of these two things to get rid of this minus. So that will become AXBZ minus AZBX. And now we're fine. Okay, cool. So, what now? Well, this isn't bad. And what we could do is we could substitute this back into the original and we could get, you know, a term for CX. But I'm not going to do that just yet. What I'm actually going to do is I'm going to divide both sides by these brackets. Okay, and the reason for that is because now I'll have CY over AXBZ minus AZBX, and this will equal CZ over, and then this will be AYBX minus AXBY. And you know what? I'll let this equal to lambda. Okay, now why is that useful? Because now I have that CY equals to lambda lots of AXBZ minus AZBX if I compare these two, and if I compare these two I'll have CZ equals to lambda lots of AYBX minus AXBY. Okay, now what I can do, big reveal, is now I can put these two things back into this equation, or either of them, and now I can get CX in terms of lambdas and all the other A's and B's. So I've got, what do I have? Well, I've got I've got BX AX CX plus, and then I've got BX AY lots of CY, which is lambda lots of AX BX minus A. Oh, careful, that's a Z. It's AXBZ. And that's AZBX. And then this, and then add BXAZ of CZ, which is going to be lambda lots of AYBX minus AXBY, and this equals to 0. So first thing we can do is we can get rid of the BX's because we multiplied that by everything there, so that can go. And now I'm just going to get CX as the subject. So I'm going to get CX equals, and then when I minus this whole thing and minus this whole thing, then essentially I can just get them to the other side and swap these brackets around, take a factor of -1 out. So I'm going to have AY, lots of lambda, lots of AZBX minus AXBZ, plus AZ lambda lots of AXBY minus AYBX. And then all I have to do is divide by AX. So divide that by AX. So all of this has to be divided by AX. Like so. Okay. First of all, is there anything that cancels? Well, if you think about it really carefully, really carefully, I've got an AZBX there and an AZBX here with an AY, and there's an AY. So, and because this is a plus and this is a negative, these two terms are going to cancel out. That's nice. Next up, what do I have? I've got an AY times by this stuff, but then I'm dividing by AX, so that term goes. So I've actually got lambda lots of minus AYBZ here. And then over here, I've got AZ times AXBY. But then this AX is going to cancel with this one. So I've actually got plus lambda lots of AZBY. So now, drum roll, I've got CX equals lambda lots of, and then this will be AZBY minus AYBZ. And actually, you could have jumped to that straight away by symmetry if you really wanted to. So now what I'm going to do is I'm going to take all of my equations here and whack them here like that. So now I have got, in terms of A and B, what my vector CX, what my vector C would be. And remember, my vector C was just CX, CY, CZ. Now notice, because they're all being multiplied by lambda, and this normal vector isn't unique, it could be scaled up or scaled down, I could actually eliminate for lambda straight away. Okay, and if I just wanted a vector and not scaling up or scaling down, I could just compute all this. Okay, so now here's the trick. That means C is the same as, and now in vector form, it would be this vector times by I, because that's the I component, plus this vector times by J, plus, and this is the Z component, K. Oops. And you're probably thinking, right, okay, so what? Why is that useful? Well, because now imagine the following. Let's suppose I've got the vector I, J, K, and now I put in one row the column vector of A, which is going to be AX, AY, AZ, and then in the next row I've got BX, BY, BZ. What happens if I take the determinant of this thing? Well, remember our 3 by 3 determinants when we did matrices? You'll have I, lots of, and then because we're doing I, we'll cross out the I row and I column, and then we'll do AY, BZ, here it is, minus AZ, BY. And if you look, we're actually a factor of -1 out from here, which is nice. Okay, let's crack on. And now remember, for the next one, we're in the second row, first row, second column, and remember this plus minus checkerboard. So we've actually got minus J, lots of. And now we've got AX, BZ, minus AZ, BX. And again, this is a -1 out from here. And similarly, for the first row, last column, from the K column, it's going to be plus K, lots of AX, BY, minus AY, BX. And you can clearly see that that is a factor of -1 out from this one. Okay, now for all intents and purposes, right, we have found the normal vector. Now why is it you're saying, well hold on, everything was being multiplied by -1, what gives? Why is that? Well, what's actually happened is that must have corresponded to this lambda being -1 originally here. Remember how there was a lambda there and we just divided it by lambda just to get rid of it? Then technically, if I put a lambda in front of all these things, because of what we've got, then if lambda was -1, then this satisfies this perfectly. And now, I'm hoping you'll see that if you take the determinant of the ijk column vectors across the top, and then one column vector in another row, and another column vector in another row, and you take the determinant of that, you will get the normal vector. So this whole thing, you will actually get the magnitude of n. Not n hat, n. Okay? And that clearly is the magnitude of A times the magnitude of B times sine of theta, because that's the area of the parallelogram. Okay, so essentially that's how you can compute the vector cross product. Okay, now, so the determinant is the area scale factor, and we've just done the scale factor, and that's clearly the parallelogram. And it also outputs a normal vector. That's why we've got to times it by a little normal vector going on here. So if you want a demonstration of how this would work, then let's consider the following. If I've got the vector I, and by the way I is 1, 0, 0, and I've got the vector j, which is the vector 0, 1, 0, then what do you think would happen if I crossed I and j? What do you think should happen? Well, what's the only vector? Shouldn't this be k? Because the area of the parallelogram of I and j is just 1. So I want a vector of length 1 that's popping out from I and j. That's I and that's j. And clearly that's just 1k. So let's try this. It's the determinant of I, j, k. And then we'll put the I column vector, so that's 1, 0, 0, and the j column vector, which is 0, 1, 0, and we'll take the determinant of this thing. So it's going to be I lots of. Well, cross out the I and I, you've got 0 times 0 minus 0 times 1, so that's a big fat 0. So you've got no I. Minus j, lots of. Cross out the j column and j row. I've got 1 times 0 minus 0 times 0. That's also a big fat 0. Plus k lots of, and now we cross out the k row and the k column. I've got 1 times 1 minus 0 times 0. That's a 1. So I'm just left with k, as we'd expect. Okay, so this was an example. Okay, now that proof wasn't needed. I.e., you don't need to know where it came from. It's good for you to know, but essentially it just comes from taking the dot products and comparing it to the determinant of a 3 by 3 matrix with one of the rows. Or in all fairness, you could have, you know, if you wanted to do A cross B, you could have easily done I, J, K with AX, BX, oh geez, AY, AZ, and this is BX, BY, BZ, and take the determinant of that. Oh dear. You could have easily taken the determinant of this, that's fine, or you could have made them rows just like I did up there. It honestly doesn't matter. In actual fact, I think most Americans, North Americans, like Canadians, I think they do it that way. It honestly doesn't matter. The determinant will be the same. Because you can evaluate the determinant by any row or column, so it's honestly not going to matter. Okay, so couple of key properties. Key properties. First of all, it's not commutative. and that is orientation matters. So if I do I, so e.g., what do I mean by that? If I do I cross j, that will give k. But if I do j cross I and the other way around, that will give negative k. Okay, so the order matters. The order matters. And pretty much think of your right-handed coordinate system. Okay, with this. So, you know, if you do I cross j, then you push your fingers out to I, you close them to j, and where your thumb's popping out, that's where the normal vector is going to be. So in more general terms, if I do A cross B, this is the same as minus B cross A. So that's pretty much that in a nutshell. Okay. What else have we got? Well, we've actually got the following. The volume. Now, what did I say up here? I think this was wrong. Now, the area of the parallelepiped, that's wrong. Okay. Now, when you take the determinant of this thing, it's not necessarily going to be this. Okay. With parallelogram, it's fine. We take the determinant of that thing, and essentially, yeah. But with 3 dimensions, it's not so straightforward. Now, if I want the volume of a parallelepiped, it's the following. So if I've got, let's say, a parallelogram looking like that, where this vector is B, this vector is A, and let's suppose I've got another vector pointing out like that, where from here to here is C. So let's say the vectors A, B, C are popping out and forming this parallelepiped, then the volume of this parallelepiped would be A dotted by B cross C. And the way you do that is you evaluate the cross product first. So do this first, and then whatever that result is, then dot it with A. Okay, and when it comes to associativity of this, or distribution, then you've got to be really careful because the order matters. So the way I like to think of it is if you can take a letter and you can slide it to the front of the queue, then that works. So A cross B dot C, that's also the volume of it. Or if I took, let's say, the other way around, if I wanted B at the front of the queue, then what would I have to do? Well, I'd have to move A all the way to the front like that. In which case C cross A dotted with B would be the same thing. So there you have it. If you were to get the order wrong, you would get the negative volume and it just wouldn't make sense. But essentially, if you just want to take the magnitude of this, you'll be fine. Just be aware that commutativity doesn't work for vector multiplication. So be careful which way you're doing things. Okay. Now there's various other things with the vector and cross product. I could tell you the angle between the shortest distance between 2 lines. I could tell you the angle that 2 planes meet, and so on. That is a bunch. Honestly, that is such a bunch of stuff that you don't necessarily need to memorize. I will say this, however. Say you want to find the angle between 2 planes. Okay, if you want to find the angle between 2 planes and you have no idea to start, then what you do is you find the angle between the 2 normals to the planes. So say, for example, I've got a sheet looking like this, and I've got another sheet kind of popping out like this, and they kind of intersect in a line. then if I've got a normal of this sheet popping out like this, and I've got the other normal, say where it intersects with the sheet, popping out like this, then the angle between the two planes would just be the angle between the two normals. Okay, and you'd use the dot product, okay, on the normals. It's far easier. Okay, if you want to find the shortest possible distance, then please remember that that the object you're dealing with has to be perpendicular. Okay. A few other takeaways. For example, if you cross product a vector with itself, then essentially you've got a vector A, and then you're crossing it with the vector A again. So how big is the parallelogram? The parallelogram is 0. Okay, and similarly, if you try and do something cute like A dotted with, let's say, another vector B crossed with A, then this is also going to be 0, because as I said before, you could shuffle this around and preserve the orientation of the order. So it becomes this. And then, well, what could happen then? Then I could move the B to the front like that, and then it becomes B dot A cross A, and then that's still 0 by up there. So just be aware that if you've got a vector dotted with, and then that vector again crossed with something else, yeah, this is always going to be 0. Okay. There's lots of things to take in for this, and to be honest, I'm just going to do a bunch of examples so you get the hang of it. But how to compute the vector and cross product, and using this normal vector for the Cartesian, they're the coefficients of x, y, and z, the Cartesian coordinates of the plane. So I don't know. Say I've got a plane. Let's say I've got a plane with vector. Actually, no. Let's say I've got a plane with I don't know. Let's say I've got a plane with Cartesian form. Let's say x plus 2y plus 3z, and let's say that equals to 6. Okay, and I want to turn this into vector form. Okay, so suppose I want to turn that into vector form. So this is a plane. I want it into vector form. First of all, the normal vector is just going to be the coefficients of the terms in front. So this is clearly 1, 2, 3. Okay, what else? Well, there's multiple things you can do here. One, you just need to find 2 vectors that are on the plane. Or you just need to find 3 points and construct 2 vectors. And it's really easy, because let's suppose you let x be 0, y be 0, then what must z be? Well, 3z is 6, so that has to be 2. What about when x is 0 and z is 0, then 2y is 6, so that's 3. And then let's suppose that y is 0 and z is 0, then x equals 6. Hurrah. Now all you've got to do is say that the pi is just going to be a point on the plane, so 0, 0, 2, plus some arbitrary multiple of one vector, plus some arbitrary multiple, which is a different letter, we'll call it mu, of a different vector. So let's suppose for this first one, I just go from this vector to this vector. How do I do that? 0 to 0 and the x component is 0, 0 to 3 is 3, and 2 to 0 is minus 2. Done. And suppose for the last one, then I just want to go from the first one to the last one, say. It doesn't matter. Then from 0 to 6 is 6, from 0 to 0 is 0, and from 2 to 0 is minus 2. These are not unique. I could have scaled the 6 and minus 2 down, so this could have been 3 and minus 1, and this would have been a perfectly valid equation of a plane. Notice how you can only scale down, only scale these two down. Do not scale the first one, because that corresponds to a point on the plane. Okay, so if I've got x plus 2y plus 3z equals to 6, then that's one way of turning it into a vector form. Suppose I had it the other way around and I didn't know what the Cartesian form was, then it's very simple. I want to find the perpendicular normal vector, so I take the determinant of ijk of one vector, which is the orange one, so 0, 3, minus 2, and then the red one, which is 3, 0, minus 1. And then I take the determinant of that. This will give me the normal, so this will be I, lots of. And then it will be 3 times minus 1, which is minus 3, times by 0 minus 0 times minus 2, which is nothing, so that's going to be a minus 3. And then I've got minus j, lots of. And then I'm going to have 0 minus 1, which is just nothing, minus a 3 times minus 2, which is minus 6, and minus a minus 6 becomes plus 6. So that becomes positive 6. And then finally I've got k, so I'll cross out that one. And I've got 0 times 0 minus a 3 times 3, which is a minus 9. So clearly, now that I've done the determinant, it should be pretty obvious now that the normal vector I get from this is I is minus 3, j is minus 6, and k is minus 9. And I can scale this up and down as much as I want to, so if I divide by minus 3, then 1, 2, 3 is valid. I now know that it's just 1, 2, 3 dotted with the x, y, z will equal a constant k. And clearly that just means I've got x plus 2y plus 3z equals to some constant. And all I need to do now is substitute in a point, and let's pick this one over here from the line 0, 0, 2. So when this is 0, this is 0, and z is 2, then 3 lots of 2 means k equals 6. So that means I have x plus 2y plus 3z equals to 6. And everyone's happy because that is exactly what we had up there. Okay, so all I did was just made up a plane, I turned it into a vector form, and then I went from that vector form and went back to Cartesian. Really simple. Okay, I'm just going to go through 3 examples, I think, and then I'll leave you to it. So, if you really want to, give this one a go. Pause the video, and we'll give it a try. Okay. The points A, B, C have position vectors A, B and C respectively relative to a fixed origin. It's given that A is I plus j, so that's 1, 1, 0. B is 3i minus j plus k, so that's 3 minus 1, 1. And C is 2i plus j minus k. Okay, find B cross C. Okay, B cross C is just going to be the determinant of I, j, k, and we're going to have 3 first, that's 3 minus 1, 1, then C next, which is 2, 1, minus 1, and I'll just do it. So it's going to be I lots of, well, I've got minus 1 times minus 1, which is 1, minus 1 times 1, which is minus another 1, so that's a 0, plus, oops, negative, remember, because it goes plus minus, j lots of, and then 3 times minus 1 is minus 3, minus a 2 times 1, which is minus 2, so you've got a minus 5 there, plus k lots of, and then I've got 3 minus a minus 2, so that's plus 5. So I've got no I, minus minus 5j and 5k, so I actually have 5j plus 5k is B cross C. Okay, so that's my answer for the first one. Then it wants me to calculate A dot B cross C. So now I need to do 1, 1, 0 dotted with BC, which is 0, 5, 5. Clearly this is 1 times 0 plus 1 times 1, which is 5, plus 0 times 5. So the answer is just going to be 5. Part C, find the area of the triangle OBC. Well, that's quite easy, because if I've got a parallelogram where that's B and that's C, then the triangle BC is just half the parallelogram. So when I did the cross product, I got 5j plus 5k. So that gave me the vector 0, 5, 5. So the magnitude of this thing, and then halved, will give me the triangle. So I've got 5 squared plus 5 squared square rooted and then halved. So that's 50, and 50 is 25 times 2, so it's going to be 5 root 2 all over 2. So the area of the triangle is just 5 root 2 over 2. Work out the volume of the tetrahedron. Interesting. Now A dot B cross C is the volume of the parallelepiped. Okay. Now, interesting fact, the tetrahedron is 1/6 of the parallelepiped. Okay, and you may need to think about that y yourself. You can split this up into 6 equal parts. Essentially, it's a deformation of a triangle. Let's say I've got a cuboid like that, you know, and I've got a point in the middle. I can make a pyramid like that. I can make a pyramid like that, a pyramid like that. There's 6 pyramids here. There's the base one, there's the one there, there's one popping out in the front, one on the side, one at the back, and one from the top pointing downwards. So the tetrahedron would just be one of these pyramids, say the base one. There's 6 of them, so it's a 6th. So really, the volume of the tetrahedron, OABC, is I take the cross product, which is this thing, and then divide it by 6. So the volume actually is 5/6. So it's 5/6 units squared is the tetrahedron OABC. Just let me make sure I haven't made any mistakes here. B is 3 minus 1, 1. C is 2, 1, minus 1. If I've taken the determinant correctly, it's 1. Yeah, that's 0. And then minus 3 minus 2 is minus 5. Yeah. 1 times 0 is 0. 1 times 5 is 5. 0 times 5. Yeah, okay. Yeah, fine. I'll just leave it there. Cool. Okay, next question. Pause the video, give it a go yourself. Okay, the lines L1 and L2 have the equations blah and blah. If L1 and L2 intersect, find the value of alpha. Okay, so what have I got here? If they intersect, then that means I can solve a set of simultaneous equations. So if I read across the top, I've got 1 plus lambda times minus 1, which is minus lambda, equals 2 alpha plus no mu. So alpha is 1 minus lambda. Okay, solving the next few lines, I've got minus 1 plus 3 lambda equals 2 minus 4 plus 3 mu. And I've got 2 plus 4 lambda equals to 0 plus 2 mu. If I take the last row and divide by 2, then I've got 1 plus 2 lambda equals to just a single mu. Then I can plug that up here in this row to get minus 1 plus 3 lambda equals to minus 4 plus 3 lots of mu, so that's 3 lots of this thing, which is 3 plus 6 lambda. If I minus 3 lambda from both sides, I'll get a 3 lambda on the right hand side. Minus 4 plus 3 is minus 1. Ooh. So 3 lambda is 0. So lambda is 0? Interesting. If lambda is 0, then alpha is just 1. Okay, well let's see where that takes us then. If lambda is 0, then mu is 1 as well. And if mu is 1, let's just see what's happening then. Then the point of intersection should just be 1 minus 1, 2 then, if lambda is 0. So then we've got alpha, which is 1 minus 4, 0, plus 1 lots of 0, 3, 2. 1 plus 0 is 1, minus 4 plus 3, yeah. Nope, seems legit, it's consistent. Okay, Fine, easier than expected. Okay, find an equation of the plane containing the lines L1 and L2, given your answer in the form blah, where A, B, and C and D are constants. Okay, right. So really, A, B, and C are the coefficient. Those coefficients are normal vectors of the plane. So we need to do the cross product of the directional component of the line L1, which is minus 1, 3, 4. So I, J, K up there, take the determinant of this. And then the directional component of this, which is 0, 3, 2. So let's do that. So I've got I lots of stuff minus J lots of stuff plus K lots of stuff. So for the I's, I've got 3 times 2 minus 3 times 4. So I've got 6 minus 12 is a minus 6. For J's, I've got minus 2 minus 0, so that's a minus 2. And then for the K's, I've got minus 3 minus nothing, so that's a minus 3. So it looks like I've got the vector minus 6, positive 2, minus 3. They've got no common factors, so I'll leave that as n. In actual fact, I could make 2 of them positive by making 6 minus 2 positive 3. And the reason I'll do that is because now this is the same as 6x minus 2y plus 3z plus sum d equals to 0. And I know a point that's on the plane because I know a point that's on both of the lines, and that is just 1 minus 1, 2. So when x is 1, I've got 6. When y is minus 1, I've got minus 2 times minus 1, so that's plus 2. And then when z is 2, I've got 3 times 2, which is plus another 6, plus a d equals to 0. So what is that? D is minus 14. So the equation of the plane appears to be 6x minus 2y plus 3z minus 14 equals to 0. And they could be multiples of each other, right? You could have had 600x minus 200y plus 300z minus 1400 equals to 0. You know, it doesn't matter as long as they're multiples. So that's fine. Okay. For other values of alpha, the lines L1 and L2 do not intersect in the skew lines. Yeah, makes sense. Given that alpha equals 2, find the shortest distance between the lines L1 and L2. Okay, let's draw a sketch and think about what's going on. So, here's my line L1, and here's my other line L2 running under it like so. Okay, what do I know about these two lines? Well, the shortest distance is going to be where there's a point here, let's call it A, and there's a point here, let's call it B. And if I was to draw a line between these two, I would know that this would have to be 90 degrees, and that line would also have to be 90 degrees to L1. Okay, so, let's try and work out what these points would be. Well, A, we're going to need some more paper. God, it's very hot in here. Sorry if you can hear the fan, it's just very hot. Okay, so what's going on? Well, the point A would just be a general point on the line L1. So how would I go from A to B? Well, that would be the general point on the line L1. Well, that would be B minus A. So I would do alpha minus 4, 0, which is 2 minus 4, 0, minus the 1 minus 1, 2. But then I've also got to add the directional component of L2, which is mu lots of 0, 3, 2, minus the thingy bob component lambda 1, 3, 4. Okay, let's tidy this up. 2 minus 1 is just 1. Minus 4 minus minus 1 becomes minus 3, and 0 minus 2 is minus 2. And this becomes plus mu lots of 0, 3, 2, and minus lambda lots of 1, 3, 4. Okay, this is the general A to B. And I know if I dot that with L1, that will equal to 0, and I know if I dot it with L2, this will equal to 0. So dotting it with L1, it just means I'm going to dot this whole thing with 1, 3, 4, the directional component of that, and set it equal to 0. And I'm going to do the exact same thing here, but this time I'm going to dot it with the directional component of L2, which is just 0, 3, 2. And now I'm just going to set up a pair of simultaneous 6 simultaneous equations, and this will give me some mu and some lambda value such that it will give me a unique lambda and unique mu for where the points are, and then once I know the points I can do 3D Pythagoras, and this is quite easy. So the first line is going to be 1 lots of 1 plus no mu minus 1 lambda equals to 0. Yeah, can you see that? Because I've got 1, whoops, if I just do the dot products on this, I'm going to have 1 lots of 1 plus mu lots of 0 minus lambda lots of 1. And clearly that's going to be 1 plus no mu minus 1 lambda times by 1 equals to 0, so straight away, lol, I know lambda is 1. So although this looked a bit confusing and stupid, actually it's going to simplify out pretty quickly. If I look at the next line, I've got 3 lots of minus 3 plus 3 mu minus 3 lambda equals to 0. I now know lambda equals to 1, so minus 3 lots of lambda is just minus 3. Well, I can divide by 3 everywhere, so I've actually got 3 mu minus 6 equals to 0, so it looks like mu is just going to be 2. So now I've got the lambda and mu of what I wanted. I sub it into the original bits at the top up here, so when lambda is 1, I've got 1 minus 1, 2, plus 1 lots of 1, 3, 4, which is going to be 2, 2, 6. And then when mu is 2, I've got alpha is 2, so hold on, I've got 2 minus 4, 0, plus 2 lots of the directional component, which is 0, 6, 4. And this is going to be 2 plus 0, which is 2, minus 4 plus 6 is 2, and 0 plus 4 is 2. Oh wow. This is going to be really easy, because then the distance is just 2. Because if you think about it, it's going to be the change in the x component, so 2 to 2, so 2 minus 2 squared, plus the change in the y's, well that's 2 minus 2 all squared, and the change in the z's, well that's 6 minus 4 all squared, and then 3D Pythagoras that. So this is a 0, this is a 0, 6 minus 4 is 2, 2 squared is 4, square root that, the distance is just 2. So they're a distance of 2. So this distance here is just 2, and at that point there, that's where lambda is 1, and that point for B there is when mu is 2. Nice. Okay, last one. So, pause the video, give it a go yourself. The position vectors of the points A, B, C relative to an origin O are blah 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 blah. Find AC cross BC, find the area of the triangle ABC, and an equation of the plane ABC in the form of R dot n equals P. Right, first of all, the area of the triangle ABC is just going to be a half of my previous answer, which is AC crossed BC, but the magnitude of it, because I don't know if it's negative or positive. Fine, and find equation of the plane ABC. Well, this thing will just be my n, and I can just do the dot product. This is really easy. So first of all, what is, let's define some things. What is A to C? Right. Okay, well, hold on, let's not skip steps. So that's where I make mistakes. Every single time I make mistakes, it's because I'm skipping steps. Every time. So let's write this out. So A is 1 minus 2 minus 2. B is 7i, no j's, and minus 3k's. And C is 4i, 4j, no k's. Okay, A to C is to go from 1 to 4 is going up 3, to go from minus 2 to 4 is going up 6, and to go from minus 2 to 0 is up 2. And then B to C Let's go from 7 to 4 is minus 3, from 0 to 4 is up 4, and from minus 3 up to 0 is positive 3. Have I done that right? Yes. Okay, now to cross them, to cross AC, I just need to take the determinant of I, J, K, and then I do AC first, which is 3, 6, 2, then BC, which is minus 3, 4, 3. And yeah, I just find the absolute value of this thing. So let's just do that. So I, 6 times 3 is 18, minus 2 times 4, which is 8, minus J lots of, and then I have 3 times 3, which is 9, minus 3 times 2 is minus 6, there's going to be minus 6 there, then plus K lots of, 3 times 4 is 12, minus 6 minus 3 is minus 18. So I have I times 18 minus 8, so that's 10I. 9 minus minus 6 is 15, so it's going to be minus 15J. Then 12 minus minus 18 is 30, so it's going to be plus 30K. So AC cross BC, like this, is just 10I minus 15J plus 30K. The area of the triangle ABC, that's going to be easy, because now I just take 3D Pythagoras on the cross product, so that's 10 squared plus a minus 15 squared plus a 30 squared, and then square root it. Calculator time, so I cannot be bothered. So 10 squared plus 15 squared plus 30 squared is that, and if I take the square root of that, I get exactly 35, and that is going to be the area of the parallelogram, remember? So the area of the triangle, ABC is just going to be 35 over 2 units squared. So that's my answer for that one. Okay, part C. Let's turn this off. An equation for the plane ABC in the form r dot n equals p. Well, I know the normal is going to be 10 minus 15, 30, because that's the cross product, and it's saying if I dot it with some r, that's going to equal some constant p. Well, do I know any points on the plane ABC? Yes, I know a few of them. Well, let's pick C, because the numbers are nicer, 4, 4, 0. So apparently, if I do 4, 4, 0 with this, I should get a constant. So 4 times 10 is 40, 4 times minus 15 is minus 60, 0 times 3 is nothing. So this is minus 20. So actually, r dot 10 minus 15, 30 will equal minus 60. Or if you want that p to be positive, what you could do, if you think about it, is you could do r dot with the negative of this. Well, in actual fact, let's scale things down a bit. 10, 15 and 30 I could divide by 5 to make this a 2, minus 3 and 6. If I did that by 4, 4, 0, what would happen? I'd have 8, minus 12 and nothing, and so what happened there is that becomes a minus 4. Notice how dividing by 5 took 60 down to minus 4. Essentially, we're dividing by 3 lots of 5. Interesting. Next up, what could we have done? Well, in actual fact, if I wanted to make this a positive 4, then if I made that a minus 2, plus 3 and a minus 6, this would be a minus 8, a plus 12 and a minus 0, so that would be a positive 4. So if I now write minus 2, 3, minus 6 and equals to positive 4, I now have an equation of the plane that we tend to like. We like the equation of planes equaling to positive numbers, although this form is perfectly valid as well. That's still the correct answer. It's not a unique form. If you feel the need to tidy things up before presenting them, then generally speaking, you want the constant of that end thing to be positive, but it doesn't particularly matter. Okay, hope you had fun, and yeah, toodaloo.